All right, you guys, today we are going to talk about probability simulations. Okay, now one thing really quick before we get started. These slides, when I upload them to Google Classroom for you, you don't have to do anything with them other than read through them. Okay, they're just notes for you with examples. Okay, so let's start with the vocab. What does simulations mean? Now, obviously there's different kinds of simulations, but we're talking about probability simulations. So when we talk about probability simulations, they're basically experiments that are designed to model some kind of real life event that would be really impractical to actually perform. Okay, they allow us to represent the probability of these events by using an experiment with similar probability. Okay, so that's a lot of information in one go. We're going to go over examples, but as just like a quick intro, let's say that you, for some reason, want to roll a dice 1,000 times, because everyone wants to do that. Instead of actually rolling the dice 1,000 times, though, you could simulate those results using a random number generator. So we know that a dice has 6 equally likely outcomes, right? We know that there's 1, 2, 3, 4, 5, and 6, and they're equally likely. You can actually design a number generator online or in Excel or whatever program you prefer to have 6 equally likely outcomes. So you could use these numbers or any other 6 numbers. And then basically just push a button and it will run the simulation 1,000 times for you. So you don't actually have to roll the dice 1,000 times and record results. It'll do it for you. Okay. So most people would think that, rolling a dice 1,000 times is impractical, which is why it's so cool. We have these things called simulations that can basically represent the same probability. Okay, so let's go over a few other examples in detail. So we're going to start with the multiple choice test. So let's say you're taking a multiple choice test. We know that theoretically there's 25% chance of randomly choosing the correct answer if there's 4 choices. We want to know what simulation we could represent this situation with that would have the same probability as the multiple choice test. Okay, so what other event or experiment could we do that would have the exact same outcomes? Okay, so I'm going to go over how I think is the easiest way to go about answering these questions and what to look for. Okay, first thing to look for, I would suggest looking for, how many outcomes are there in the original event, right? The problem actually tells us twice. If you read through it, there's theoretically 25% chance, right? So we want something that has 25% chance of randomly choosing something. It also says 4 choices, right? So 4 choices, 25% each, right? So here we want something with 4 outcomes. 4 outcomes equally likely. So 25% each, right? Okay, next thing I would do is think, right? You're like, yeah, duh. Think about what else has 4 equally likely outcomes. Okay, so it could really be anything as long as there's 4 outcomes that are all equally likely to happen, right? So for example, maybe we know about a program online that has a 4-section spinner that has equal sections. Pretend that those are all equal sections, okay? Let's see here. These colors do not go very well together, but that's okay. So we know that each section has 25% chance of being landed on when spun. Okay, if we have a little spinner. Okay, this would be a lot easier to do than actually going through a multiple choice test, right? So let's move on for a second. There are other options, right? Again, I said it could be anything as long as there's 4 outcomes that are equally likely, right? So here's a few other examples for you. So we already said the 4-section spinner, right? With 1 section assigned to each of the multiple choice answers. So if we have our spinner, I won't color it in this time. Again, pretend that it's they're equal sections. Maybe we assign that one to answer A, this to answer B, C, and D. Okay. You spin it. If it lands on B, that's the one you would record, right? You could maybe use a 4-sided dice if there is such a thing. I'm sure there is, right? And assign each side. One side is assigned to each multiple choice answer, same as we did right here. Okay. Again, you could always use a 4-number random number generator, right? So you go to a program, a random number generator program, say you want to use 4 numbers, 1, 2, 3, and 4, and you're going to say that 1 would be for answer A, 2 would be for answer B on the multiple choice test, 3 would be C, 4 would be D. All right, so each of these have 4 outcomes, 4 outcomes, same as the original, right? And they're all equally likely to happen. Okay. All right, let's go over another example. It's probability, so obviously we had to talk about weather. Terrain or not terrain, that is the question. So let's say we have a weather report, and the weather report shows that there's a 50% chance of rain. What simulation could we use to represent the same probability? So I'm going to go through the same steps as we did last time. So first thing I would look for always with these questions, how many outcomes are there in the original event? Again, the problem will tell you, right? 50% chance of rain. If there's 50% chance of something, it means that it's going to be 50-50, right? 1/2, meaning there are 2 outcomes. Okay, the 2 outcomes in this case are rain or no rain. Okay, so we want something with 2 outcomes that could represent the weather report, right? So, next step is to think. What is something else that has 2 equally likely outcomes? This one's even easier than 4 outcomes. There's so many things that we could use for 2 equally likely outcomes. For example, actually, we'll just go over to my examples and I'll explain each of them. Okay. So, for example, we could flip a coin, right? We know that coins have I don't know where I was going with that. Coins have a heads and they have a tails. There's the lovely building. Okay. Heads and tails. Ooh, sorry about that. Those are my dogs. So 2 outcomes equally likely, heads and tails. We can assign each outcome, heads or tails, to one of the outcomes in the original problem. So maybe heads represents rain and tails represents no rain. Okay. Oh. Okay. Another example, another simulation we could use is a 2-section spinner. Right, we saw the spinner before in the last problem. Maybe we assign the right side of the spinner to rain and the left side of the spinner to no rain. Right, so this also has 50% chance of happening and 50% chance of happening, right? So equally likely outcomes, same as the original problem. right? But doing a spinner is going to be a lot easier to demonstrate than trying to change the weather, right? You could also do a 4-section spinner, or really any number that you can cut in half, right? So maybe we still say that, I mean, it's a 4-section spinner, yes, right? There's 4 sections, but maybe we still say that the entire right half or left half is rain and the entire right half is no rain. Okay, so really anything that you can split in half. Anything you can split in half. Okay, another example of that particular genre would be this example, a 6-sided dice, right? We know a dice has 6 outcomes, which is different than 2 outcomes. Hello, stating the obvious. But we can actually split those numbers up, right? So maybe we say that the numbers 1, 2, and 3 represent rain, and 4, 5, and 6 represent no rain. Or maybe we say that odd numbers equals rain, and even numbers is no rain, right? So anything you can split up into 2 different sections or 2 different outcomes that are equally likely could be used for this particular problem as a simulation. Okay, hope that's clear. Let's go over one more example. This one's a little more complicated. So let's say that we have Mr. and Ms. Sargent who have 4 boys. Every time people notice this, they comment about the odds of this happening. The Sargents decide to set up a simulation with 10 trials to determine this probability. So we want to know what simulation we could use for this. Now this one's a little more tricky because we've got a few different parts here. We have a few different parts. I keep clicking the wrong button. There we go. We have 4 boys, right? So we're going to have not only different outcomes, but we need to have like 4 separate experiments going on within our one experiment. Sounds a little complicated, but we'll walk through it. We also have 10 trials. So let's go through this a little more detail. So I broke this one up into different questions for you. Hopefully that will help. All right, first question. What simulation could be used to represent the likelihood of having a boy or a girl? So let's just assume that they are equally likely to happen. We're not going to worry about genetics and stuff right now. We're just going to assume that they're equally likely to happen, right? So we want something with 1 outcome, 2 outcomes. So we want 2 outcomes. Okay, so again, we are looking for how many outcomes there are, right? And next we're going to think about what type of simulation could be used for this. Now, basically we could use any of the ones we used on the last example, right? So you could do a 2-sided spinner, right? Maybe that's boy, girl. You could do a dice with odd numbers or boys, even or girls. Really anything that has 2 outcomes that are equally likely. Okay. Okay, so let's say that we, however, decide to, instead of the ones I just mentioned, we're going to actually flip a fair coin. Okay, so we have heads with the face on one side and tails. We'll do a little building. That's my lovely building for you. Here, we'll draw a tree. There's a tree. Heads and tails. 2 outcomes, equally likely. Okay. The next question then would be, which outcome represents having a boy and which represents having a girl? It's important to decide this beforehand, right? We can't just, run our experiment and say, oh, well, it landed on boys and I really want to have a boy, so I'm going to use tails for boys, right? You have to decide ahead of time. Okay, so in this case, let's say that we'll do tails is going to represent boys. And we're going to do heads that represents girls. I believe that's what I wrote on the next slide. So again, you have to choose ahead of time. Yep. Heads girl, tails boy. Okay. Oh, don't get too dizzy here. The next question then would be, how should the simulation be designed in order to account for 4 different children? So if we only had one child, we could just say, let's flip a coin 10 times for the 10 trials, right? One flip is one trial. However, in this case, we have 4, right? We have 4 different kids. So we have to design it so that we get outcomes for each child. So how to do that? Good question. I'll walk through this answer. I know it's kind of a lot to read, so I'm going to walk through it for you. See, it's green. Okay. So we could, if we're tossing a coin, you know that heads is girls. I'm just going to rewrite that. Tails is boys. Okay. If we toss a coin 4 times, 4 tosses, actually, I'm going to write this out. So toss number and result. Okay. So we're going to toss a coin 4 times. Each time represents a different child. So this is, kid number 1, kid number 2, kid number 3, and kid number 4, right? So if we toss that coin 4 times, that gives us results for all 4 kids. I'm just gonna, I don't know. We'll just go with that. Okay, but that is only, remember the other part of this question was, we want 10 trials, right? So this right here, this could be considered one trial, right? One trial is 4 tosses of our coin. So each toss is a kid. Each toss, need more space here. Each toss is a different kid, different child. Okay, but we want 10 trials. We want 10 trials total. So if we have 10 trials total and we know that each trial has 4 tosses, how many coin tosses are we going to have total? We are going to multiply to find out. 10 times 4 would be 40. So 40 tosses total. And that would give us the outcome for having 4 different kids that are all boys. So that's the probability of having 4 boys. Now, obviously, the more trials you have, the more accurate that probability is going to be, right? The closer it's going to get to theoretical probability. But in this case, the question only says 10 trials, so that's what we went with. Okay. Okay. I hope those examples help, but let's just review the important information really quick. Simulations, again, basically allow us to represent the probability of real life events that would be really hard to actually do, right? Like tossing a coin 1,000 times. And they allow us to do this by using an experiment with similar probability. Experiment with similar probability. So if it's a 50-50, you use something with 2 outcomes, right? If there's 4 outcomes in the original event, you use 4 outcomes in the simulation, right? So number of outcomes should be the same. The same in the simulation as the original event. That's probably the most important thing you can remember, okay? The number of outcomes should be the exact same. Okay, the other things when you're asked these types of questions, so like, which simulation could represent this situation? Again, there's key things to look for. Look for how many outcomes, right? Same thing that I was just pointing out. How many outcomes? And then think about what else has that many outcomes. Okay, if you can remember those things, you should be totally set with simulations, matching simulations to probability of real life events. Okay, if you have questions, just let me know.